Right, thanks, Marion. So I'm going to be talking about a project that I've been a part of for the last 6.5 years called BOUT++, and the various sustainability things that we've done in it. I don't think anything's particularly novel or mind-blowing. Is sort of the story of our journey and some lessons I've learned along the way. So first of all, the software that I'm talking about is called BOUT++. It's a framework for solving fluid equations with a heavy emphasis on plasma modeling. It has been used for aerospace and astrophysics and chocolate, so it's not just plasmas. And it's basically a domain-specific language embedded in C++ so that researchers can write fairly natural-ish looking equations like this on the bottom left, which produces stuff like that on the right, which is the technical term is a blob, a bit of magnetized plasma in the scrape off there of a tokamak that mushrooms out like that. So that's the software. I joined the team at about 2014, the end of 2014, as a computational physics research officer, which, as far as I'm aware, was globally unique. And I, learned a bit about software engineering. I'd done a PhD and then postdoc, 1.5 postdocs by that point, and I joined BOUT++, and I thought, they're doing it right. It had a test suite, it had a ton of examples, it's got a LaTeX manual, it's got a nice build system that AutoConf, everybody knows configure and make probably. It had a development workflow model with pull requests, and I was like, "Wow, this is, this is what proper scientific software should look like." At this point, I don't think I'd even heard of the word software sustainability. It was another year or two before I found out about research software engineering. I was like, "Oh yeah, that's what I do." So that was the state of it when I joined, and so. I think that was a really solid base for sustainable development. And I think if every bit of scientific software that I came across looked like this, I would be really happy. But obviously, I'm going to talk about the improvements we've made. So fairly early on, I realized that, okay, it's got this pull request workflow, but it wasn't always followed. There were, I don't know, a dozen or so active collaborators on the repository, and everybody that had write access could push straight to master. I tried to dig out the numbers. From what I can tell, 10 pull requests were opened in 2014, so the year before that I started. But there were about 45 merges straight into master. That's actually really tricky to find out from Git, it turns out. And so obvious solution, lock the master production branch and require pull requests. That ensures everything that gets merged into the production goes through a pull request, can be reviewed by the maintainers, and you can hang all the various other technical enforcement processes off the pull request. And so the year after I started, there were 50 pull requests. There were 200 last year. And so the lesson from this is that sometimes there are technical solutions to cultural problems. People not following the workflow, you can technically enforce that. That's possible. The next thing, I said it's got a test suite. There was about 18, I think, integrated tests. Some testing subsystems, some testing full physics models and looking for regressions. It had to be run manually by developers. It took at least 10 minutes if you built it, optimized build, and even with the pull requests enforced, we still sometimes merge stuff that perhaps didn't even compile. Again, pretty obvious now solution. Use continuous integration or continuous development service. We started on Travis. We've now moved to GitHub Actions. There's tons of these. That got the test suite running automatically on every push to the repository. Even with that test suite, there's just integrated tests. It catches the most obviously broken code, stuff that doesn't even build, stuff that really breaks things. We just catch and we can say, we need to fix this before we merge. And a lesson from this: automate the automatable. We've got other things now. We've got linting and static analysis. Got formatting. on other projects, like Python projects, you can automate the packaging and uploading to PyPy. I think this is pretty standard lesson. Automate everything that you can, really. The next thing was that, okay, we've got all these integrated tests. They slow. They take long enough to make a cup of tea and drink it. And they're broad. If you're running an entire physics model and it breaks, where is the problem? So two solutions to this. I think the sort of obvious one, add unit tests. I gave a version of this talk in about 2017, and we had 300 tests at that point. And I just checked last week, and we've got more than 2,000 tests, unit tests, and they take less than 10 seconds. No, they take about 12 seconds to run. And they point, exactly where the problem is. As a different solution that is also important, I think, is that having good version control discipline, where you make atomic commits that they do one thing and they're orthogonal. They don't do multiple things. They just do one working thing. That have good commit messages. Commit messages are documentation. They're sometimes the only documentation that certain people will actually write. So it's important to do those well. And you can't enforce that technically, right? I don't know of any system that will make sure that somebody has written a good commit message. That's a cultural problem that there isn't a technical solution to. And you need to educate and teach and train people to write good commit messages. The next thing is that, okay, so it took some time for me and the community to learn how to do things well. And I think there's been about 40, 50 collaborators and contributors to BOUT++ over the years that have come through. And some of those have, cut their teeth on BOUT++ in the last few years, new PhD students. And this is like the first proper scientific software they've seen. And we're doing things, I think, pretty well sustainably. And so they learn how to do things like, this is how you write software, and they go out and they do new projects and they take those lessons with them. So in the BOUT++ wider project, there's the central library, and then there's various grid generators and post-processing utilities around it. And some of those have been around from the beginning, some are new, and the newer things, have got all these things, all these sustainable development built in. They're doing things right from the very beginning. And there's all these other things that the community members go on to work on, and lots of this stuff is immediately transferable. It doesn't matter if you're writing C++ or Python. Writing automated test suites, continuous integration, you can apply that to any project. And so the lesson from this is that the community is important. That the making sure your community is educated about good software development techniques has this network effect, and they affect dozens of other projects. And so that brings me on to my very last point. I'm very lucky this year that I got one of the EPSOC RSE Fellowships that I'm starting next week, 1st of July. And basically the aim of my fellowship is to try and encourage researchers to share their software and data in the plasma science community across the UK. And so I want to do that by basically trying to improve the sustainability and usability of basically every single bit of software that I can get my hands on. I'm aiming with a network that I'm going to form of other plasma RSEs to try and improve hopefully 100 to 200 different projects over the course of 5 years. Right, that's me done. Here's my conclusions. Thank you for your attention. So for this in particular, I was talking about the researchers and the RSEs, they worked on BOUT++. So lots of, because it's like a framework that requires you to write some C++ to actually use it, lots of the users are also developers. There are people that just use physics models that other people have written, and they can be less involved in the software development. So we've got a lot of researchers who do write code. So that community of people, helping them see how to do things sustainably, I think was really important, because they're going on often writing their own post-processing stuff and making sure that they test their physics code that they might not have learned if they've come through the academic route. For things like testing, which I've just been recently trying to convince a new community to testing is quite important. It's faster to write tests. I know it takes time to write the tests, and it takes time to settle this stuff up. But once you've got it set up, it's much faster to get to a solution that works, and that you're confident in, right? That I'm sure everybody has come across the case where you discover a bug and you're like, well, that's been in there for a month, 3 months. And so all the work that I've done in that time period is suspect. Even if the bug doesn't affect it, it's suspect because until you go and check all those cases, you don't know. So having those tests in place means actually it's much faster to get to that paper that you're confident you're not going to have to issue an errata to. I think if I was starting a new project, I'd just switch to main. I'm very aware of the reasons for switching. I think, and they're very sensible reasons. I'm aware of a couple of projects that I used that have switched, and their switch, it was ripping off a plaster, If you've done it, it's actually fine. But for a new project, main, I think is, I saw lots of arguments about it will break lots of code, but that actually Git doesn't. Math is just convention, and I think there's a variable that's like, what is the default branch? So you should be using that anyway. I just don't think that really describes the relationship as well.